Hello everyone, and today we're going to be talking about image filters. We have covered the basic building blocks of an image, the pixel, and in this video we will be talking about how we can perform operations on pixels to extract important information. So first off, we have this thing called monadic operators. So what they are is some function that you apply to a single pixel. So we have some input image, we take a single pixel from that input image, we apply some function to it, and we get some output image. So some examples of these are like change in contrast or thresholding, where if it's above a certain value, we set it to white. If it's below that, we set it to black, or you can change in brightness where you change the value of every pixel up or down. While monadic operators are very simple and easy to use, often what we need is some function that represents the neighborhood of pixels rather than just the pixels themselves. This is what we can see here. So we're taking here is some small subsample of all the pixels around a certain pixel. So this is our center pixel, and these are the values around it. We're taking some function on all of those pixels to output a single pixel in the output image. So we take in many pixels from the input image to render one in the output image. An example of that is averaging using a linear filter. And we're going to replace each pixel by a linear combination of its neighbors. The matrix of the linear combination is called the kernel. So this is the thing that we're going to multiply all of the subsections of the image data by. So what we can see here is we take every single value from this local image data and every single value from the kernel and multiply them together and then sum across it all. So you get 10 times 1 or 5 times 1 and so on all the way down. So the output that we get from using this averaging kernel is a 4 at the center location. So what we do when we actually take a real image is we take this kernel and we apply something called a convolution where we go across the entire image. Now the question you may be having as we go through this is what happens when the kernel falls off the edge of the image? And there's lots of different ways of handling this. And it mostly just depends on application. So you can fill it in with zeros, you can fill it in with the nearest value, you can fill it in with white, whatever makes sense for the actual application that you're talking about. This is some examples of some different linear filters. So here we have the identity filter, which is just a 1 in the center because you get out the exact same image. We can have one that shifts it to the left by 1 pixel. We can have one that shifts it to the right by 1 pixel, or we can have something that does a blurring effect, like we were talking about earlier. The averaging kernel we talked about earlier is a specific example of a larger class of kernels called smoothing kernels. And these are very important for computer vision applications because they allow you to reduce noise. We're going to see a little bit more what this looks like later on, but essentially what you're seeing is a blurring effect. So often when we're talking about smoothing kernels, it makes more sense to focus in on specific parts of the image. We want pixels that are closer to the pixel that we're looking at to have a higher weight than the pixels after it. So we get this thing called a Gaussian kernel, and essentially focuses on a central point. So we care more about pixels that are closer to the pixel we're outputting than pixels farther away. So this is the output of what a couple different Gaussian kernels look like of different sizes. So this is a Gaussian kernel of 1, so just the identity, or 5, or 10, or 30. The next thing we talk about is edge detection. One of the things we're often trying to find in images is where there are edges, because edges typically lead us to important information. So before we get into edge detection, we have to talk a little bit about calculus. So you probably all remember from calculus, the derivative of a function is the slope at some instantaneous point. Now this makes a lot of sense if you're talking about a function of a single variable, but often in robotics we're going to have functions that have multiple variables in it. So what we can see here is some function f, which takes in a variable x and a variable y, and what we want is how does f change as the value of x changes? And this is what we're kind of seeing here. So you have some manifold that represents your essentially function values over some xy plane. And what we're going to be looking at is how does it change along this green line here at the center. This is kind of the idea of what a partial derivative is. We're going to be focusing a lot more on these in week 4, but the basic idea is as one value changes and the other one remains fixed, how does the function change? So what we're actually looking at when we do edge detection is we're going to try to approximate a partial in a specific direction, and what you get is this equation down here at the bottom, where essentially it's the value of 1 subtracted by the value of another divided by 1. So as we can see here, that's exactly what we do when we do an edge detection kernel. Some partial with respect to x, we're going across this way, or some partial with respect to y, so we're going down like this. So what are we actually doing when we do edge detection? As I was talking about earlier, we do partial, but kind of here's a zoomed in of what that looks like. So we have some image, we have some line going across that image with what we're looking at, and we're just going to plot the values. So as you see in the center here, so you have some white values, and then it goes to black, and then it goes back to white. And if I took the derivative of that function, what I would get is something that corresponds to a negative derivative and then a positive. So I get a negative derivative and a positive derivative. And what this corresponds to is an edge. So anytime you have a spike in the derivative, you have an edge. So there's a couple of different kernels that we often use for edge detection. They get a little bit better results than just doing what we talked about earlier. So these are like Sobel or the Pruitt. There's other more advanced detection algorithms like the Canny edge detector, which uses a combination of different things, but we will not be talking about that today. So why does edge detection often fail? So if you see here, we have some function f of x, which just represents a single line across our image, and it's very noisy. There's a lot of jumps. So if I took the derivative of this function, what I would get here is down at the bottom. It's this very spiky graph, and I cannot tell where an edge begins or where an edge ends, even though in the original image it is very obvious where the edge should lie. So what I'm going to do here is I'm going to do a smoothing kernel. So I'm actually going to be using this Gaussian smoothing kernel here, the second graph. So I take my signal and I'm going to convolve my Gaussian kernel across it. What I get out is this smooth third graph here. Now looking at the bottom graph, if I took the derivative of the third, I would get the fourth. And from the fourth, it is very obvious where the edge is. By doing a simple smoothing operation, we have taken a very noisy signal and converted it to a very clean edge detector. So here's a visual representation of what that looks like. Often if you take some image without smoothing and you just apply an edge detection kernel to it, what you'll get is all these artifacts up here in the top, where you kind of don't really see the outline of the person very well. But if after you do the smoothing, you'd apply it again, what you get is a very clean output. Image filters are good for extracting simple geometric or color-based information. They're quick and easy to implement, but are often black box systems. That means there is no easy solution to solve the problem. What combination of filters will work for a specific task always comes down to the domain knowledge of the person creating the filters. Tuning or playing around with the parameters is the best way to get reliable results.